All right, ladies and gentlemen, welcome to our section on graphing the other four trig functions, tan, cotangent, cosecant, and secant. All right, so we're going to be using some asymptotes today. You recall that cotangent, cosecant, and secant are all the reciprocal functions, so you might be thinking a little bit about secants, reciprocals and what those things might end up being. And we're going to start off with tangent, cotangent, and we're going to start right away with tangent. So for tangent and cotangent both, they have periods of pi. This is very important because these are the only two trig functions that have a period of pi. The other four have periods of 2 pi. So when we want to find the period, I get period equals pi over b. Right? This is very important because you guys are very familiar with doing 2 pi over b and not pi over b. All right? So for tangent, cotangent, this little fraction is very important for us. The other values of a, b, c, and d, they all affect the graph in the same way as they do for sine and cosine. So a determines how skinny our graph is, basically how tall and stretched out it is. You'll see what I mean in a few minutes. C helps us figure out our phase shift. It's still the same. It's C over B. And D is our vertical shift. It moves our center line up and down, up or down. And what we're going to first look at is tangent of x. So we're going to look at the function tangent x. My writing is going to be a little bit ugly today as I am using my mouse. So if I was to look at a table, it's kind of an ugly Y, so let's try that again. Okay. What I want to do here is I want to go from negative pi halves. I want to go negative pi fourths. These are our 5 special numbers here, just like we did for sine and cosine. These are my 5 special numbers. We're going to go 0. We're going to use pi fourths. And we're going to use pi halves. All right, so we're dealing with tangent. And what you might notice in here is some very interesting things. First of all, tangent of negative pi halves, so negative 90 degrees. If you go to your circle, or if you use your hand trick, whatever you want to do here, the tangent of negative 90 is 1 over 0. And 1 over 0 is undefined. And if we get an x value that makes an undefined y value, this should make us think asymptote. And it's very important. Okay, tangent of negative pi fourths, which is the 45-degree angle in quadrant 4, is negative 1. Tangent of 0 is 0. Tangent of pi fourths is 1. And tangent of pi halves is undefined. So what does that mean for us on a graph? I'm going to pretend I know how to use the straight line tool here. Hey, look at that. All right, so seriously. So here we go. I'm going to be out here at pi halves. I'm going to be out here at negative pi halves. And let's go ahead and start plotting everything we know for these particular numbers. All right, so I'm going to start here. I'm going to create asymptotes at negative pi halves positive pi halves. And then I'm going to put my little dash in here for pi fourths, and my little dash in here for negative pi fourths. And then I'm going to plot the other dots that I know. I know I have a 0, 0. And be up here at 1, down at negative 1. And I have a dot here at negative pi fourths, comma, negative 1, and positive pi fourths, or positive pi fourths, and positive 1. And here's where you got to do a little trickery. This kind of ends up looking like a cubic function. So this is going to come up, and it's going to be ugly because it's on the computer here. But you guys, I hope, are kind of bearing with that right now. And as best as I could, that looks like a tangent function. I might even suggest that you guys graph this on your calculator, kind of look at this. You'll notice that this is not the only piece of the graph. There are things that continue to happen to the right and to the left. If I went out another pi halves, so if this was pi, I'd have another asymptote out here. I know I'm right up along the side here, but you get the idea. And you're going to get another piece that looks like this. It's going to look identical to this other piece that we just drew here. So what you want to notice here is the distance between negative pi halves and positive pi halves, or the distance between two asymptotes, is pi, or 1 period away. So this is period. All right, so it's very important that we understand the distance between two asymptotes is 1 period. Okay, so this is tangent of x. Let's go ahead and move on to cotangent. Cotangent works exactly like tangent. And what we're going to do, I know that was a little quick there, but we're just going to do the same thing we did for tangent. And I'm going to make a big table here. So if I started with 0 in the middle, kind of like I did for tangent, and I go negative pi fourths, negative pi halves, pi fourths, and pi halves, you get some interesting things going on here. So here's part of a problem. At 0, tangent was 0. But if tangent was 0, that means the reciprocal cotangent is undefined. Okay, so cotangent of pi fourths is going to be 1. And again, you can use your hand trick. You can use your circle. If you're using your circle, it's the x coordinate over the y coordinate. And then cotangent of pi halves is going to be 0. Well, I need two asymptotes to define 1 period. So I need to go farther. I need to go 3 pi fourths. And I need to go to pi. Which means tangent and cotangent are not centered on the same number. They're not centered at 0, 0 anymore. Or cotangent's not. The cotangent of 3 pi fourths is going to be negative 1. And the cotangent of pi is my other asymptote. So because it's kind of shifted to the right a little bit, I'm going to do this. Now what I want you to notice here is I didn't use either of these numbers here. So the 5-point strategy for cotangent is going to be these 5 numbers. It's going to be 0, pi fourths, pi halves, 3 pi fourths, and pi. Okay, so go back to my pen. Here's pi. Here's pi halves, pi fourths, and 3 pi fourths. And at pi, I have an asymptote. And at 0, I have an asymptote. Kind of hard to see a 0 asymptote, huh? And then at pi halves, I'm at 0. Pi fourths, I guess I need a 1 up here. And a -1. And again, this is going to kind of look like a cubic function. Only downward instead of upwards, a downward slide instead of an upward slide. And again, go ahead and verify this for yourself on your calculator. Instead of writing cotangent, you can't write what cotangent, so you have to do 1 divided by tangent of x. And you should get this basic kind of graph, downward cubic, right? It won't show you any asymptotes, but again, notice this. The distance between two asymptotes is pi, which is equal to my period in this case. So if my period was pi halves, the distance between two asymptotes is pi halves. So what if I wanted to shift this over something? So let's say let's just go with tangent because it's the same thing as cotangent. If I had the tangent of x minus pi sixths. Well, let's think about that, what that would look like. All right, so the period here would be pi over b. So my period is pi because there's no b value. But my phase shift is pi 6 to the right, which means I need to go pi 6 to the right. So let's call that pi sixths. Well, I need to go this direction pi units. Well, pi units from pi sixths is 7 pi sixths. So I need 7 more of these little dashes. 1, 2, 3, 4, 5, 6, and 7. Okay, I can get rid of this thing now. So this is pi. Now, here's what we need to figure out is like where do things get shifted? Where do things get shifted for tangent? Well, here's where I just go back to the standard function, the base function, the parent function. Normally, we have an asymptote at negative pi halves. But that asymptote has to be shifted to the right pi sixths units. So my new asymptote is pi 6 to the right. Also, likewise, on the other side, normally my asymptote is at pi halves, but I have to move pi 6 to the right. And I get those lovely asymptotes there. Now, you notice I haven't really done there's no need for tables. It's another one of those things where we can think about the halfways and the quarters. Well, normally we start at 0, 0, but we have to go pi 6 to the right. And guess what? That's halfway between my two asymptotes. And then tangent is an upward slide. So halfway between my middle point and my asymptote, I have to be at my max or min, or quote-unquote max min. It's not really max or min. But because the amplitude here is 1, I'm going to be here at, oops, it's not a downward slide. It's an upward slide. And halfway here, I'm going to be up at 1. And then I can connect my dots. Again, sorry for the ugliness. And there's kind of a basic one period of the function. All right. So I'll link some more videos, probably to Khan Academy, on how to graph sine, cosine, tangent, cotangent. Hopefully he'll do a good job of giving extra examples, and we'll have our in-class time as well. All right, so let's move forward to cosecant and secant. Now, here's why we do all four of these functions in one section. Tangent and cotangent are new. However, for cosecant and secant, if you can graph sine and cosine, you already have basically everything you need to know for cosecant and secant. So I'm going to reiterate this. Cosecant and secant both have periods of 2 pi. So in order to find the period, you're going to do 2 pi over b. And we'll probably end up looking at this particular function in a few minutes, but here's why. Cosecant is related to sine. So if you get a cosecant function, you can start by using what you know about sine as a guide for cosecant. And again, you'll see what I mean in just a second. Okay, so we're going to start with cosecant of sine, or cosecant of x. And I'm going to kind of write out a few things here that you guys might need. Wherever sine crosses the x-axis, or the center line, the fake x-axis, that's where cosecant has an asymptote, because that's where sine is 0. And here's the other parts. Each maximum of sine is a minimum of cosecant, and each minimum of cosecant is a maximum of cosecant. Or sorry, a minimum of sine is a maximum of cosecant. Take a minute, kind of gather your thoughts for that, and we're going to move to graphing cosecant. And we're going to say cosecant from sine. I'm going to start with the basic 1 period, maybe a little bit more, of sine. So let's call this 2 pi, which makes this pi, which makes our other stuff our pi halves. And let's go out a little bit farther and call this 3 pi. Not a whole lot of necessity for 3 pi, but I'll show you why I want it. All right, so let's think about sine. What do we know about sine? Well, I know that sine starts at 0, 0, ends at 2 pi 0, halfway is in the middle. Here we go. Up 1, down 1. All right, so goes up first and down second. Now what I'm going to do is I'm going to continue this pattern to the right all the way over to 3 pi. You'll see why in a minute. All right. You do not need to draw in sine. What I did was the main 5 points are going to help me graph cosecant. Because from those statements that I gave earlier, it says everywhere that sine crosses the middle line, which in this case is the x-axis, it creates an asymptote for cosecant. So every time I cross the x-axis here, in this example, is an asymptote. And then for my other statement, it said wherever sine was a maximum, so right here at pi halves, cosecant is a minimum. Well, in order for it to be a minimum, it's going to look kind of like a parabola here. And then everywhere sine was a minimum, cosecant has a maximum. And that I just drew here, not including this stuff over here, this right here is one full period of cosecant. Notice I have a trough and a mountain piece. Okay, so a valley and a mountain. You're required that for one full period. You'll notice I have my ones just like I would for my sine curve. I have 0 to 2 pi. In this particular case is one full period. And I could just continue this pattern. Obviously, this would be right over here. It's not necessary for one full period. That's why I kind of drew it junk, right? Blame it on the fact that I didn't need it. And I'd continue again. There'd be a down, and then there'd be an up, and then there'd be a down, all right? And you'll notice the distance between two asymptotes is half of the period. So the distance between 0 and pi is pi, which is half my period. All right, so like I said, notice I started with sine. I saw what did sine do, and then used that to graph cosecant. Now what I want to do is also, I want to do the same thing for cosecant. Or sorry, we did cosecant. Let's do secant. So let's do secant. Secant x, we're going from cosine of x. If I do the same thing here, I'm going to first make it so that stuff works. Okay, I'm going to go out to 2 pi. I'm going to be there at pi. There's my pi halves. There's another pi half. And here is 3 pi. Okay, so let's think about cosine. Remember, we're starting at cosine. And remember, it sets up exactly like sine does. Only this case is cosine starts up, and one period away, it ends up. Now, I've seen this a few times as people are thinking that it just goes down to this point here in the middle and then it just goes back up. But the problem is you need a maximum at 1 and a minimum at -1. Well, for cosine, my maximums occur at my beginning, my ending. Remember, this is for parent. My minimum occurs halfway between. And then my x, oops, that was ugly. My x-intercepts are my quarters, or my halves, I guess, in this case. And again, don't bother putting this in there because it's actually not part of my secant graph. But what I want to do is I want to say, oh, look, it crosses the x-axis here, which means that's an asymptote. And that's an asymptote. Well, it's exactly the same thing for secant as it was for cosecant. This is a maximum point for cosine, and therefore it's a minimum for secant. Notice I'm only graphing this side because I'm showing what the thing looks like between 0 and 2 pi. All right, this minimum for cosine becomes a maximum for secant. And this maximum becomes a minimum. Now, this is one full period. Notice it has an entire upward one an entire valley, I guess, if you want to call it, and an entire downside one. Now, if you are uncomfortable with leaving these little half parabola things, just continue this picture. I missed a little bit. Continue this picture, and you get this. You could continue this side as well. And you'll move up like that. Okay, this is actually a period and a half drawn like this, all right, because we have an up and a down and another up. So if you really feel like it, we can be a little bit more adventurous, and we can draw in another one here. And I know you guys are all adventurous and more graphing, right? I know you are. Don't lie. All right, so that is 2 full periods of secant, in case you were wondering. But really, I like to, that's why I started with 0 to 2 pi, because that's really like one rotation around the circle. All right, so always start off with, for secant and cosecant, always start off with their reciprocal functions, sine and cosine. Okay, just as we did here. And at least find the 5 points for the cosine version or the sine version. Right? So if we were to do something like secant of, let's go 2x minus pi halves. All right? This tells me my period is pi, and my phase shift is pi fourths. Okay, pi halves divided by 2, pi fourths. And it's to the right. All right, so I'm not going to deal with the secant of this function, or secant version. I'm going to deal with the cosine version, because I know that cosine goes from 0 to 2 pi normally. But let's say that's 2 pi, let's say that's pi. And I hope you all can figure out what my other dashes are going to be here. I need some sort of pi quarters, so I'm going to go all the way down to pi fourths. So here's pi halves. So I'm going to deal with cosine, because really I want the reciprocal of cosine. So cosine is going to look like this. Let's go up here to 1 and down to -1. Cosine is going to start up at pi fourths. And then 1 pi away, well, that's over here. Halfway is going to be my minimum. And my other halves are going to be my x-axis crossers, my x-intercepts. Well, I'm not going to draw the cosine function because that's not what I want. I want the secant function. So I'm going to draw my asymptotes. And then I'm going to use that minimum as a maximum. I'm going to use this. Let's go ahead and, where's this other dash going to end up going? That dash line should go right there at -pi fourths. Another reason I'm going to do that is because then I can actually get a good parabola looking thing here. And just because I like to do it, let's go, what is this, every 2 dashes is my asymptote here. And obviously yours are going to look a lot better because you're going to use graph paper and all that sort of fun stuff. So you might start understanding that secant and cosecant are really easy to graph once you've gotten the hang of sine and cosine. Because if you've got sine and cosine down, secant and cosecant, they should just kind of snap and be right there. Tangent and cotangent, those are really your new ones. But you follow those examples from before, you get my help in the morning, you'll be successful as well. But there you also can't give up. I've been seeing a lot of people in the class, they're just kind of giving up, or it's kind of looks like they want to give up because it's graphing and it's hard, or they claim it's hard. It seems like a lot of people just want to give up on graphing, and I really hope you guys just kind of step it up, show me that you can do it, and show others that you can do it. Help others as you get going. All right, so you guys have your assignment sheet. I just put this page here because I felt like it. I'll see you guys in the morning. I hope I helped a little bit, and have fun.